In this video, we're going to look more intently at our three kinetic and energy tendency terms that we found in a previous video. Specifically, we want to look a little bit at this geostrophic geopotential flux term, which we've already looked at a little bit earlier in the semester, but then also our baroclinic conversion and our barotropic conversion terms to talk about how this gets manifested in the atmosphere. And so let's go ahead and start with this geostrophic geopotential flux term. And so in order to consider our geostrophic geopotential flux, we need to draw ourselves an upper level wave pattern. And so let's go ahead and do so, but we're not going to draw one that is then uniformly distributed. And so we need smaller waves to then bigger waves. Okay. And we'll draw a series of three lines here. There we go. So what we need to consider now is this term that we have up here, our minus del dot phi prime UAG vector. So we're going to go ahead and read that. Minus del dot phi prime UAG vector. Right, so it's this multiplication of, let's make sure we get a prime in there. There we go. Of our anomalous height values multiplied by the geostrophic component of the wind. Now again, we're drawing a typical scenario here, so we could say that if this was 250 millibars or 300 millibars, for example, maybe this is 900, 912, and 924, just for some examples. And so we know our geostrophic flow should move from west to east. And so let's first consider what we know to be true about our geostrophic flow. Our geostrophic flow is so based on our regular flow, right, U, we have then both the geostrophic component and the geostrophic component. We know that around our ridges, our flow is faster than what geostrophic flow would predict, such that our VAG component would be to the west, or to the east rather. Around our troughs, they would be slower than geostrophic, and so our geostrophic component would actually be in the opposite direction. So if that's our scenario, and that's true of all of our troughs and ridges, so around our troughs, the geostrophic flow is to the west, and around our ridges, the geostrophic flow is to the east. Let's couple that with what should be our phi primes, right? Around ridges, we know that phi prime should be greater than 0, right? Because the height values are higher than the average, say, at this latitude belt. And around our troughs, phi prime is going to be less than 0. And so we can then couple that with our understanding of our VAG. VAG, if it's going to the east, VAG is also less than 0. And around our ridges, VAG would be greater than 0 because it's going to the east. So it turns out then that when we have our combination of these two multiplied together, they are both going to be greater than 0 around our ridges, since both values are greater than 0. And around our troughs, we have two negatives, and we know that two negatives make a positive such that the combination is greater than 0. And so that in each one of these terms, if we were to draw this vector, this phi prime times UAG, which is still going to be a vector, our vector would always be pointed downstream. And the size of the vector is going to be dependent on the strength of the anomalies of either the geostrophic or the geopotential height anomaly, or the combination of the two. So then to look at this term, right, this is the divergence, basically, of the geostrophic geopotential flux, such that we need to then look at the relative strength of our green arrows then as a result of this term. And so we know that downstream of this ridge, right, more is fluxing out of this ridge, so that our downstream troughs and ridges should grow. And this is that idea of downstream baroclinic development. And that this ridge then, since less is fluxing in and more is fluxing out, that we are getting net divergence of energy from our ridge and things that precede it, and that convergence of a geostrophic geopotential flux downstream. And again, this is a manifestation of this idea of downstream baroclinic development. And now we see more distinctly that it falls out of this idea of kinetic energy and energy flow through our atmosphere. So it's not super surprising. Next, we want to move on to our baroclinic conversion term. Here, what we're really talking about is our low pressure. Our low pressure centers that we might have our warm front and our cold front. And again, we have then some temperature isotherms associated with this. And we have our moist tropical air out ahead of it, and we likely have our CP air behind it, CP air out ahead of our warm front. They might be slightly different CPs, but we get the picture. And so what happens with the cyclone circulation, right? We have our primary circulation here associated with our cyclone, right? Our cyclonic rotation. But that from this, we get our temperature advections. And so we generally get our warm air advection around our warm front and our cold air advection with our cold front, which we know leads to rising motion patterns on this side, on our east side, and sinking motion patterns on the west side, such that we've developed a secondary circulation. The stronger the gradient, the more available potential energy. The more available potential energy, the more kinetic energy in terms of these vertical motions. And so from our circulation, we use the available potential energy available within the temperature gradients, i.e. the baroclinic nature here, to generate our kinetic energy, these circulations, both our primary and our secondary circulation. And so the stronger the temperature gradient, the stronger the jet we get aloft, the stronger kinetic energy. We can also then change the shape of the trough and ridge, which then will change elements here as well. And eventually we can't maintain the temperature gradient. We're using up that available potential energy, and our cyclone weakens. And so we can see the development of our available potential energy in the building up of our temperature gradient, and then through generation of the kinetic energy in our jet streams and our circulations, then weaken the temperature gradient once we've used up that available potential energy. And so that is our baroclinic conversion term. Our barotropic conversion term is all about our generation of eddies due to the flow itself. And so here what we're essentially doing is we are saying we want to take energy from zonal flow and make it into energy that is in eddy flow. So zonal flow, again, that idea of the large-scale background flow versus then our eddy flow, which is associated with a particular like circulation, for example. And so one way we can think about this is if we draw a typical jet stream in our XY plane, we have one area where we have the strongest wind, and then we have weaker winds around it. In both of these scenarios, we then generate circulations, whether in a positive or negative sense. And so where this gets most exhibited is if we think about a very strong jet stream. And what happens off of this jet stream is we get very strong winds on this north side that all of a sudden will produce eddies. And so this is a manifestation of taking our large zonal energy and creating it into eddy energy. In a future video, we're going to look at some satellite imagery that exhibits this idea of this barotropic conversion of taking large-scale zonal energy, which is generated from our zonal potential energy, and then converting it all the way down to our individual eddies in this eddy kinetic energy sense. So this was just a little bit of a look into these three terms to see how this energy is flowing throughout the atmosphere. Thanks for watching.